As always, when I work through these things, if I don't make sense, I prefer you just go ahead and interrupt me. You can either post it in the chat, or of course you can just unmute yourself and ask me a question. It does not hurt my feelings to be interrupted. So just always remember that. I prefer to make sense than anything else. But yes, I'm recording this, so when this is all said and done, you can go back and view my recordings and see anything that may need further kind of explanation, or go back and just pause it to see how I'm using the formulas and that kind of stuff. If you've been coming to boot camps, you know that in this particular unit, which you can find these formulas on page 56, but in this particular unit, there are some formulas that I'm just not a fan of that don't necessarily help you or give you any kind of advantage in using them. So again, just to remind us, the binom.dis formula, I'm against it. I recommend that you don't waste your time trying to learn it. The reason why is binom.dis.range does everything the other one does, and it's generally considered easier to use. So I really recommend you learn that one and use it. We talked about that in the previous boot camp. If you missed the previous boot camp and you want that information or that video, just send me a message privately. I'll send you a copy of that presentation as well. This week is all about norm.dis though. And so we're going to talk about how to use this formula and its counterpart called norm.inverse. So the one up here as well. And we're going to learn how to use these two. And of course, there's other functions on here, and you're going to learn today that I recommend that you don't use those functions either, that we avoid like the plague norm.s.dis. They work just fine, but there's no mathematical advantage in using them. So you're going to find that I don't bother wasting my time using .s.dis. And I'll explain why during the test prep workshop, but essentially there's no actual material advantage. And so it's just an extra formula or two formulas that you'd have to learn if you use them. Where in this case, you really only need three formulas: the binom.dis.range when it's appropriate, norm.dis, and norm.inverse. And so really these are the only three new ones that we're going to talk about for this unit, plus all the ones you learned to pass. And so another one that I'm going to be drawing upon today, of course, is the standardized one. And so standardized allows us to convert from any measurement to a z-score. The bottom example, though, the second z-score formula I have listed here, uses something called standard error, and that's only when we're talking about CLT, which is not going to be until next week. So we're not actually going to use the bottom version. I just like to have all the formulas listed. So this bottom one we're not going to worry about right now because that's central limit theorem, and we're not going to talk about that until next week, either this Saturday if you come or coming Tuesday. So the main one we're going to focus on is this first one. Now, before we get into the questions themselves, or the formula, problems, and all that kind of stuff, let's talk a big picture about what we've been doing so far. So we learned in the first unit, numbers break down to two categories, primarily. We have the discrete kind of idea, whole number objects, and continuous. In the past couple weeks, we've been only focusing on discrete. We have our classical probabilities. We have our empirical, aka our relative frequencies. And we had this special case of binomial, which again, if you missed that presentation, that was boot camp number 5, and this other part was boot camp number 4. So if you missed those, feel free to send me a message. I'll send you those copies, but that's for the previous boot camps. And so these three cases were all about discrete distributions. And now, of course, today we're going to focus on what happens if the data is continuous. And we call that for now normal. You'll find out for test 3, there's other kinds. And so we have normal, which is today's boot camp. And then there's actually another special case that we call CLT, and that will be boot camp number 7. And then eventually, when you get to test 3, we're going to add another branch to this that's called a T distribution, but that's not relevant for this test. So for this test 2, we need to know about these 5 different cases and how to calculate the probabilities. We've already done the 4th and 5th boot camp, and of course today is all about the 6th one. And so this is what we're going to focus on today, the normal distribution case. And so some things to note about it. If you remember normal distributions, that's just a bell-shaped distribution that is symmetrical. So we have something kind of like this, not a great drawer. And so the first thing we want to notice is in the center here will always be our average, our mean. So that's our main center here. And then what we're trying to do is if I find out some observation, maybe the observation's on this side, doesn't matter really, but let's just say it's on that side. I can either find the probability on less than X, or I could find the probability greater than X. And the really cool thing with Excel is Excel does all the hard work for you if you know the command. And so if you ever want the probability less than X, where X is less than, let me write that less than symbol a little nicer, less than some number. The cool thing is that it's just going to be norm.dist of that number, whatever that number is, given our known mean and our deviation, and always, always true. For this class, it will always be true for norm.dist. And then what do we know about distributions? What do we know about the accumulation, this piece plus this piece? Well, all distributions have to add up to 1. And so if I did the less than number with the greater than number, it has to make 1, which means if you want the greater than case, we only need to do the complement. We only have to do 1 minus the less than case. And we know how to find the less than case. So if I want it greater than some number, all I'm going to do is 1 minus norm.dist of the less than information, which is number, average, deviation, and always, always true. And so these are really the only 2 ways that we have to worry about calculating things using norm.dist. One thing I do want to point out, though, is notice I didn't consider equal to. And so why do you think that is? Why didn't I say, well, what about what happens when it's equal to a number? Or what about if it's less than or equal to a number? Or of course, the other one, greater than or equal to a number. Why did I only care about less than and greater than? Well, really think about what's happening on a continuous distribution. Notice first off that this thing doesn't close. It's always above the axis. It technically goes forever in that direction and forever in this direction, which means it goes forever to the right, or infinitely many numbers to the right, and forever to the left, so infinitely many numbers to the left. And so if I want any single number, just that one number, I would be getting that one calculation divided infinitely many times. Well, if you have one pizza and you share it with every single person that ever existed, ever will exist, how much pizza will you probably get? Virtually nothing, because you're dividing it infinitely many times, you'll get nothing. So the probability of any kind of equality in normal distribution is always going to be 0. And so what does that help us with? Well, if that's the case, remember that this symbol on the second one right here, that says less than or equal to. Well, that's an or case. That means we learned this back in classical and empirical probability. That's the probability of X is less than some number or plus, right? We add for ors, plus the probability of X equal to that number. But we just said that equal to is 0. So this thing is 0, which means that this is nothing more than saying the probability of X is less than that number plus 0. And anything plus 0 is that thing. And so it's the same thing as X is less than the number. So when we say less than or equal to, for normal distributions, it's the exact same thing as just being less than. Likewise, if I'm doing greater than or equal to, it's going to be the exact same calculation as just being greater than the number. So that's something that you don't need to worry about then for normal distributions. It doesn't matter if it's less than or equal to or less than, or if it's greater than or equal to and greater than. They're going to be the same calculation for normals. Now we know for binomials and other problems that very much matters because we're talking about objects that are very discrete and finite. But since this is infinite, we don't need to worry about it. That's the first major thing I like to point out to people. The next big concept is this other function that I mentioned that we're going to learn today called norm.inverse. So norm.dis, if you remember from my binomial discussions, .dis gives you a probability. And what kind of probability are we getting? We're getting a normal probability. So if I want norm.dis, it's going to give me a probability for the normal case. Inverse just means go backwards. You're inverting it. So essentially, this one's going to take a probability, put in some stuff, and it's going to give us a measurement. And so whatever the probability is, the exact form of it will be the probability, and then always the mean and the deviation. We don't need true for this one. But the real important thing, if you remember norm.dis automatically calculates the probability on the left side. So the one catch with this is that probability that we're talking about is a left-sided probability. So whenever they ask you, whenever they give you a probability, like maybe they'll give us 0.8 here, and this is my measurement, notice 0.8 is to the right of the measurement. We want the left side. And so that will just be 1 minus 0.8, aka the complement, to get the measurement or the probability we need to plug in. And we'll see this in action today. Just want to give us the kind of background of how all this works. So norm.dis will grant us a probability. Norm.inverse will give us a measurement. And we'll use these in context in a little bit, and of course add in some nice little wrinkles to make things interesting. So that's a big background. Let's actually dive into some questions now. I'm going to go to number 1 here. All right. So the first thing we're going to do is practice converting. So we have these measurements. Whenever we say X, we mean measurement. And we're going to convert the measurements into z-scores and then convert them to probabilities if we have a measurement. And then when we have a z-score, we're going to go backwards into a measurement and into a probability and so forth. And then finally, we're going to take these probabilities and go all the way back to a z-score and a measurement using the facts that we know down here. Now, there is a formal way that we like to write distributions, especially normal ones, and that is capital N for normal. This little line, which means distribution, so normal distribution, this kind of wiggly line next to the keyboard, or you can find it next to 1. And then in the parentheses, we always put the mean first, and then the standard deviation. So the normal distribution that we're dealing with in the first example would be written as the normal of, little wiggly line, forgot that, normal wiggly line 40 given 8. And that just tells the reader that this is the mean and this is the deviation. So if they ever ask you to represent it symbolically, they're telling you to do this. This is what they want. It's a normal distribution. There's my average, and there's my standard deviation. That's all, because this is what we need to use to calculate these things. So that's why we write it that way. And before we go further, let's talk about z real quick. What is a z? We talked about it in test 1 quite a bit, but let's just review it. A z can also be a normal distribution. So we would say n, and it represented by 0 and 1, which means that for z's, they're normally distributed with a mean of 0 and a deviation of 1. We'll need that later on when we start calculating with them, but that's essentially what a z-score is. The center is 0, and then its deviation counts by 1. 1 z-score, 2 z-scores, 3 z-scores. We count by 1, so deviations. And so, as I mentioned at the very beginning of this, if I want to go from x world to z world, if you want to go x to a z, we have a nice Excel command for that. We would just use standardize. So let's practice doing it. We'll go into that first box, click equals, type out standardize, and of course you can tab to get it auto-filling. Capitalization doesn't matter. Our X is our measurement. Our measurement was 40. Given that the normal distribution's mean was 40 and its standard deviation is 8. We're converting from the 40 world, this information down below, into a z-score. Hit enter, and there's our first calculation. And that should actually make sense because for our original distribution, the X distribution, I draw my little distribution, dead in the center is 40. That's what we're being told with this information right here. And for the Z world, its dead center, of course, is 0. And so we can see that 40 and 0 are in fact both in the same location. They're the same thing. And so that's why it does make sense that's 0, because they're the same value. 40 is the center, 0 is the center of their respective distributions. And so if I go down to 39, I would want to find out in the Z world what's equivalent to that. And so let's just convert it using our standardize command. Equals standardize. The 39, given our mean is 40 and our distribution deviation is 8. Hit enter. And there it is. And it should make sense that it's negative because it's to the left. It went down, so our value should be some number down. If we do 45, 45 is bigger than 40. So we would expect it to increase. It should be some bigger number that's equivalent. And so once again, standardize. Given 45, the mean was 40 and the deviation is 8. Close it, and there's my z-score. Let's go ahead now and take our X calculation and find the probability for each one of the ones that we just did. So what we're going to notice is this probability is asking for less than. And again, whenever we see less than, we know it's automatically norm.dist. And so it will be our observation, our X, given our mean, given our deviation, always, always true. So equals norm.dist. Our observation in the first case is 40, our mean was 40, and our deviation was 8. Always, always true. And of course, 0.5 should make sense because 0.5 is dead in the center, right? If it's in the center and we know the whole thing is 1, and I want everything to the left of the center, well, if that whole thing is being cut in half by that 40, then it should be about 50%. So 0.5 should make a lot of sense. 39 is slightly more to the left, so the probability should be less than 0.5. But let's actually verify it. Norm.dist, given 39, mean was 40, deviation is 8, always, always true. And yes, it's less than 0.5, close to it because 39 is close to 40, but not obviously the same value. Now 45 is much bigger than 40, so now I'm finding the probability starting at 40 and going all the way to the left. So I should get a calculation bigger than 50%. I won't know what it is, but it should be bigger. Norm.dist, given 45, given 40, deviation's 8. Always, always true, right? And there's my probability, about 73%. Great question, Melissa. They don't necessarily mean the same thing. It depends on the kind of data set. For a normal distribution to be bell-shaped and empirically balanced and all that, we know the mean and median should be approximately the same value. So in this context, we treat them the same way. But in non-distributions that are not normal, they're not the same thing at all. So like binomial and other kinds of distributions that we've done in the past, the mean and median are not the same thing. It's just for normal distributions, they are, because it's one of the assumptions about a normal distribution. The median and mean would line up with each other. So that's why we can utilize that 50% principle to estimate things. Just checking to see if I answered your question fully. I'm sure you'll bring it back. Perfect. Okay. Now, in the second case, we've got these z's. We want to take the z and work our way backwards to a measurement. And we're going to take the z's and calculate probabilities from them as well. So we're going to do that on these three cases that I'm drawing my little arrows from. So first off, let's think about what z means relative to an observation. Recall that the z-score, a z-score, is the same thing as the number of standard deviations away from mean. That's what it tells us relative to x in fancy talk, right? Relative to some observation. What this means mathematically is that x, our observation, is the same thing as the average plus or minus z times our deviations. So the z just tells you how many deviations you're either above or below the mean relative to your observation. So in the first case, we see that we have a 2 here. So that means this observation is our average of 40 plus, because it's a positive 2 of our deviations. So if I do 2 of the deviations and add it to 40, I'll know what the original measurement is. So the z-score is just how many standard deviations, either increasing or decreasing from the mean you are. And so when someone says z is 2, you just add it 2 deviations. And yeah, I can do that by hand, but this is Excel. Let's just take advantage of our resource. 40 plus 2 times my standard deviation, which is 56. And if I wasn't sure if I did it right, we can go backwards. We can use the standardize command. Standardize of 56 given 40 given 8. And you'll see the z-score in fact is 2. So you can always check your work. So this minus 3.4 then means that we have our mean of 40, and we're going to take away 3.4 of our deviations to get the actual observation, 12.8. And if you check it with standardized, you'll see that the standardized of 12.8 comes out as negative 3.4. Likewise, this 1.23 means I have my mean plus, because 1.23 is positive, 1.23 times the number of deviations, which is 8. 4984 is the actual observation. Now we could, of course, just go 56 down to the probability. Well, that's no fun. We want to practice using all our information. So we're going to take our z-score and calculate our probabilities each time that we just found, or just used. And so it's pretty much the same approach. Just got to be very careful what your inputs are. So I'm still trying to find a probability of less than. So I'm still going to do norm.dis. But now we're talking about going from the z world to our probability. And in the z world, what is our mean and deviation? It's no longer 40 and 8, because that's not z's. That belongs to our observations. In the z world, our mean is 0 and 1. So that's what we're going to use for our mean and standard deviation. So we have norm.dis of our z-score, in this case, because I want to do it from the z-scores, comma 0, comma 1, because its mean is 0 and deviation is 1, always, always true. And if I did it by head, because I just wanted to, I would have mean of 46, deviation of 8, always true. Notice the probability is exactly the same. So you can do it either way. It's just sometimes you won't know information about x and you'll only have z-scores, in which case you need to know that norm.dis, that its mean is 0 and deviation is 1. Always, always true. And of course you can click F4 or you can type negative 3.4, it doesn't matter. I clicked it in this case. There's my probability. And then one more time, is 1.23, norm.dis. That 1.23 number, given the mean is 0, the deviation is 1, always, always true. And there's my probabilities. Now for the last part here, so we can then start doing some word problems. So we're going to go backwards. We're going to take the probability and find a z-score and find our measurements both times. Okay, well, if we're going backwards, we're inverting the process. So we're going to use norm.inverse. And since this is all less than, that's implied to be on the left, That means that we can just plug in that probability into our function. We don't need to do anything fancy. You'll see later on when we have to do something fancy. But for now, to go backwards, let's start with the observation. Norm.inverse of our probability, 0.68 in this case. You can click on it or type it, doesn't matter. And for the X world, its mean was 40 and its deviation was 8. And that's the measurement of X. For the Z world, norm.inverse. The same probability, but now its mean is 0 and its deviation is 1. And there's my calculation in the Z world. And of course, if we checked it, if we did standardize for that X measurement, standardize of my X measurement, given 40, given 8, you'll see I get the same Z score. So these in fact are connected. They're all kind of built to each other. Let's do the last one. Let's take this to the X world first. So we're going to say norm.inverse of our probability given our mean of 40, our deviation of 8, close it. We don't need true for inverse command. Hit enter. There's our measurement. Now if I do the Z-score, norm.inverse from my probability, but Z world, it's 0 and 1, close it. And there's my respective Z-score. And so we can now comfortably go from X to Z to probability and back and forth and all that stuff. I say comfortably, at least we have an understanding of the general idea. We're going to try some actual word problems now and make sure we can do this really, really well. If you've been following me for a while, you know I'm a huge advocate of reading word problems in reverse order. That way you don't read extra information. As somebody with a reading disability such as myself, the least amount I have to read, the better. And so if I'm reading it bottom to top, I know from right here is the max information I need. Nothing above that is really that important beyond knowing its normal distribution. But they don't actually have to tell us this. You're going to find out with CLT is that it won't always tell us that when we get there next week. What really is helping us is we can see that this unit, that unit is continuous. A continuous unit means we can't use our binomial or classical or relative frequency techniques. It won't make sense because you have infinitely many possibilities. But notice what it says. We want to find the probability that it's above 25. How likely? So we want the probability. We're looking for the probability of the measurement is greater than 25. So if we just draw a brief little distribution, because sometimes they'll ask us to sketch this. In the center, we'll put our mean of 20. 25 is greater than 20, so it's over here somewhere. And we want the area to the right. So sometimes you'll hear us say the word area, and sometimes you'll hear us say the word probability. They mean the same thing as far as this class is concerned. And so if I'm telling you to find the area or find the probability, we mean the same thing. And so we want the area on the right of 25 because we want it above. Well, remember, norm.dis only finds the area on the left. So if I want the right, I simply make it the complement and I do 1 minus. Otherwise, I'll find the wrong side of my calculation. Okay, also notice that 25 is less than halfway because 20 is dead in the middle. So 25 is over here to the right of it. So this calculation should be less than 0.5 if I do it right. If I do a calculation, it comes out bigger than 0.25. I know I did something wrong. I'm sorry, bigger than 0.5. I know I did something wrong. So let's do it. Enough blabbing. 1 minus because it's greater than norm.dis. Our observation, what we're trying to witness is a socket of 25 or bigger. Given the mean is 20, the deviation is 10.5, and always, always true. Hit go, and there's our probability. It's less than 0.5, so I know I'm doing good. It makes sense in that sense. But yes, it's less than 0.5, and it's a small probability, so we're good. So long story short, if you see greater than, you do 1 minus. If you see less than, you don't. Let's try another. I need to scroll up. Here we go. Okay, so a couple vocabulary things. First one, notice we're talking about the word expect. That's our big clue that we're talking about expected value. And if you recall, there are 2 expected value formulas they expect you to know for this test. The summation of x times p of x, or n times p. And if you've been coming to my boot camps, you know that this first one is only needed for discrete table distributions, while everybody else or everything else uses the one on the right. Well, this is definitely not discrete, right? This is continuous data. So we're just going to use n times p. So we know what n is. N is the number of finite trials we have going on, which in this case is 20 individuals. But now we've got to figure out p. And we're trying to find essentially the p of this event right here. So p is an observation that's taller or bigger than 72. Well, that's greater than, right, friends? That means I need to do 1 minus because it's greater than. And of course, I want a probability, so 1 minus norm, because it's normal. This is probability. And now we just plug in what we know. We know the person is 72. We want to see somebody 72 or bigger. Given 70, given 3 from our question up top, always, always true. So we now have n, we have p, and so we just need to times those 2 calculations together. N times p. The 5.05. Do not type 0.25 there because that's rounded. Excel likes to round things a lot, so be careful. It's usually to your benefit when it's a decimal number to click on it and just don't type in what you see. Unless, of course, they ask you to round. That's different. But this is our expected value. Okay. Question, vocabulary question, feel free to put in the chat here. What exactly is a cutoff? Is it a probability or is it a measurement? What do you think? What is a cutoff? What do we mean by that word? That's right, Robert. So we have this means that we want a measurement. We want to find the cutoff. So we want a measurement. When you want a measurement, your brain should always think .inv. That will give us a measurement. So now we know we're dealing with normal distribution stuff, so it's going to be norm.inv. And the other thing we have to worry about then is this word percentile. Percentile simply means starting at the left and going until you get to that value. So essentially 0 up to the 90% of the area. And so of course the right is 10% if I wanted it. What's important though that means is percentiles are always talking about the left-sided probability. And we like it when it's left side probability because that's how Excel likes it. Excel likes the probability on the left, which means I only need to worry about norm.inverse of 90% given the mean and the deviation, and I'll get that cutoff. That will give me my measurement. And so let's get my values up here. I'm going to go equals norm.inverse of the 90th percent. So notice I don't even bother with the decimals. Let Excel do all the hard work. Given the mean is 70 and the deviation is 3. Now if you turn to 0.9, that's absolutely fine. It'll be the same answer. I just don't bother. And so that measurement is 73.8. So 73.8 is what separates the left side from the right side. And so if you wanted to check it out and make sure you did it right, you would do norm.dis of that measurement, given our facts above, 70 and 3, and true. And you'll find that that comes out to be 90%. So that does represent the lower and upper cutoff points between that. Anybody below that measurement is in the lower 90 percentile. Anybody above it is in the top 10 percentile. I would say the second part here, the middle 90%, are the ones that can be the most tricky. Now I'm going to show you all today, at least the graphical approach. In the future, I'll show you a calculation approach, but for now, I'm just going to show you graphically so you get an understanding of what's going on. And so if we want the middle 90%, that means we need two borders. One on the small side, I'm going to call it X1, and one on the bigger side, I'm going to call it X2. We want this middle part to be 90%. That means we got to be able to figure out what each of the other parts are to make it make sense. And we know that the whole thing adds up to 100%. Well, if the middle is 90, that means that these two sides have to share equally, because normal distributions are symmetrical, has to share equally 10%, because 100 minus 90 is 10. That means there's 5% on this side and 5% on this side, because 5 plus 90 plus 5 is 100. Why do I waste my time doing that? Well, remember, norm.inverse requires the probability on the left of our measurement. Well, for X1, what is the left of X1? 5%. So I need to know what that number was in order to do it. So X1 there will be norm.inverse of that 5%, given the mean and distribution of 70 and 3, mean and deviation of 70 and 3, close it, and there's that lower measurement. Now, if I go to do X2, what's to the left of X2? It's not just 90. It's all of this stuff is left of X2. Everything that's left of X2. So it's that 90 and that 5, aka 95%. So to do X2, norm.inverse 95%, given my mean and deviation, which was 70 and 3. Whoops, there we go. And there's my two measurements that separate the middle 90% out. This last one is similar to the first one, except they're saying to start on the upper side. That means if I draw my distribution, we're going to claim that this is the 0, and we're going to go 90% in this direction. So 90% over here. But again, Excel doesn't want the probability on the right. Excel needs the probability on the left. So if that side's 90%, I hope we all agree that this side has to be 10%. So that is what I'm going to be using to find my calculation. I need it on the left for Excel to work. So norm.inverse 10%, given 70, given 3, close it out, and there's that cutoff on the left side. And there's some practice with expected value and finding measurements. We'll do more, don't worry. I know it doesn't matter to y'all, but I misspelled deviation. That's going to bother me. Here we go. A little better. Okay, number 4. So let's first write out what the probability statements are for the first 3 questions, and then we'll worry about answering them. So I want the probability that 8, between 8 and 10, so 8 is less than or equal to x, which is less than or equal to 10. And we know for normal distributions, this equality portion doesn't actually matter because those equalities technically mean 0. So I could have said this instead. Probability is 8 less than x less than 10. Doesn't actually matter. Just usually when we say the word between, we're talking about an inclusive between, so we usually include the word equality. But mathematically, it's the same thing. And because it's between, our x must be in the middle, must be between them. Now we see the next part says more than 7. So the probability I'm looking for is bigger than 7. Then the probability is less than 13. So x is less than 13. And so real quick, if it's less than, we know what to do. That's going to be norm.dist. When it's greater than, because it's the opposite side, that's the right side, we need to flip it. So we're going to do 1 minus norm.dist. Use the complement rule to flip it. But we haven't talked yet about what to do when it's between, when you have two different measurements. Let's talk about that real fast. And so let's think about it. We can see for the right side, x is less than 10, right? So if I wanted to worry about that one for now, just the right side, the between statement, we would have 10 here. And if I did less than 10, that means I would do norm.dist with 10 in there. All the usual stuff behind the 10, the mean, deviation, and all that. So there's, blah, blah, blah. Well, if I do that calculation in Excel, it will give me the calculation from 10 all the way down to the end. And yes, I know technically it goes on to infinity, but theoretically the end, where it gets to. But I don't want all that. I want it to stop at 8 and not do this portion right here. Well, 8 down to the left, this calculation from 8 on down, that's nothing more than norm.dist at 8. And so if I take my norm.dist 10 measurement and I take away the norm.dist at 8, I would take off this piece right here, leaving from 10 to 8. So the good news is then, whenever we see between, we just need to do the bigger measurement minus the smaller measurement. And that will always take off that little piece at the end that we don't want, leaving whatever is in the middle. So let's do that first calculation. We're going to do norm.dist of the bigger number, and I hope we all agree that 10 is bigger than 8. And then we'll do norm.dist of the smaller number. And we're just going to write it as one giant sentence and hit subtract. In case you can't read it, that is a less than sign here. There we go. So norm.dist, the bigger number was 10. Given the mean is 9, deviation is 1.2, always true. And I want to subtract the other statement, so I'm just going to continue right on to it. Minus norm.dist of 8. Given the mean is 9, deviation is 1.2, always true. So we just write one giant sentence, big number minus small number, the 10-1 versus the 8-1. Hit go, and that's your probability between the two distributions. That's your center probability. That kind of calculation is going to become really important in test 3. For now, just know how to do it. Our next one, we see greater than, so we know what to do. 1 minus norm.dist. The number next to the x is at 7. Given our mean is 9 and our deviation is 1.2, always true. There we go. If I want less than 13, well, less than 13 is nice. We don't need the 1 minus whenever it's less than. So 13, mean is 9, deviation is 1.2, always true. Don't be fooled. Remember, Excel likes to round. So let's undo these decimals. Go to home, add in some decimals, and eventually you'll see it is in fact not exactly 1. Because if it was exactly 1, that would guarantee that people spend less than 13 seconds reading. And that's, not realistic, right? It's highly likely you'll spend less than 13 seconds reading, but not guaranteed. All right. Part 4. Reading. Boom, there's our keyword. We need n times p. Well, n is your objects, your finite trial size, your sample size. So we have 16. But we need p, and we're trying to find less than 8 seconds. So the probability is x is less than 8. Oh, wait, we know what less than means. Less than means norm.dist. So let's get it. Norm.dist of 8, given the mean is 9, the deviation is 1.2, always true. We have the p. Our n is 16, so our expected value is their product, p times n. Order doesn't matter. Robert, no, they'll never ask you for the expected value of the middle 90%. Not like that, at least. They might phrase it a little differently. But they could just have to tell you, short answer is no, that itself doesn't make a lot of sense. They could ask you, I guess, how many people would we expect to be between two values, but in the end, it still doesn't make a lot of sense because, well, yeah, I mean, technically any probability is fair game now that I said it out loud. So technically, yes, Robert, but if it's the middle 90%, that's your P already. And so 90% times how many people, you're done. So yeah, that kind of question is actually nice because they're telling you, if they say middle 90%, that 90% represents the P. And so there is no calculation. Now, could they have said how many people would be between two measurements? Yes. If I knew I had 20 people, that's my P, I could just times those together and I would find out how many people would be between measurements 8 and 10. But if they tell you how many people would have, the middle 30%, that is your percentage, that is your P. And so in that kind of case, it would be nice, they're giving you the P. So when we see percentile, we know this is the left side. And so this is 15%. There's nothing special to do. That is our probability on the left. That would be our probability on the left, which means that if we're trying to find a measurement, because this is a probability, so we want a measurement, norm dot inverse of that probability, given the mean that we know up top, which was 9 and 1.2. And the 20th percentile would be norm dot inverse, if you want measurements, of our 20% and 9 given 1.2, close it out. And again, you'll notice I never waste my time converting to decimals. I really encourage you not to either until the very end when it requires it. But like I don't bother making these 0.15 and 0.20 because I'm likely to make a silly mistake and just mess up the whole question. Okay. Part 6. We want a z-score from a measurement. We know how to do that. If you want a z-score from a measurement, that's just standardize. Measurement's 11.5. Our mean is 9, and our deviation is 1.2. So observation or measurement, mean, deviation. That's your z-score. Usual range, we talked about that last week. That will always be our center minus 2 standard deviations and our center plus 2 standard deviations. Our center for normal distributions will always be the mean. And so let's do it. We know our center from up top was 9 and our deviations is 1.2. So our usual range will have 2 measurements, of a lower measurement and an upper measurement. And so we could say our 9 minus 2 times 1.2 and our 9 plus 2 times 1.2. It was 1.2, right? Yep. And so this is the usual range, which just means that if you see values between these numbers, it's what you would usually expect. It does not mean significance. You can have a number be usual, but be significant. And once in a while, you'll get a really weird significant value that is also unusual, but doesn't have to be. So you should always be careful. Usual and unusual and significant and not significant aren't always exactly the same thing. So they tell you when they ask you for, is it unusual, they're going to usually tell you what method to use. So using the method of significance, we're going to determine if this is unusual or not. And I'll show you what I meant by that previous statement in a second. But let's actually first talk about this. So last time when we talked about the concept of significance, I told you, and it still holds, just reminding us, that when we talk about the concept of significance, we're trying to find the probability of an extreme. which in other words, a probability of a tail. And we want to know, is that probability less than 0.05? This is the question we're trying to answer. If it is less than 0.5, it is, then we call it significant. If it is not, then we say it's not significant. And so this is our significance test. Is it less than 0.05? Is it not less than 0.05? For this test, we just set it as 0.05. You'll find out that that number is arbitrary. And in future tests, test 3, we're going to modify and change that number depending on our need. But for this test, we're always going to assume 0.05. So what exactly do I mean by extreme for those who weren't here last week? Well, when we have our normal distribution, we have our center as our mean. And if our observation's on this side, then we just want to know the probability on the left. So we'd find out that extreme, the furthest part away from the mean. If my observation's on this side, then I would find the probability on the right. Always the little tail from where you're looking at. In our case, our mean was 9, and we're being asked about 10.5. 10.5 is bigger than 9. Hope we all agree there. And so I want to find the probability of this tail. I'm essentially trying to find out, is the probability that x is greater than 10.5, is that calculation less than 0.05? That's the question we're trying to answer. If it is, we would call it significant, which means you would call it unusual. If it's not, you would say it's not significant, aka not unusual. Now we can already see that 10.5 is between these numbers. So we know by the usual range, it's not unusual. Well, that doesn't mean that by significance, it's two different methods that it won't be significant. But let's keep going. We see this is greater than. So that means I'm going to do 1 minus norm.dis, because greater than is always 1 minus. The value was 10.5. Given my mean was 9 and my deviation was 3, always, always true. Probability is 0.30, 0.30. Right? You're comparing 2 decimals to 2 decimals. 0.30 is bigger than 0.05, so it's not true. It is not smaller. It's not less than. Therefore, it's not significant. So we would say 10.5 is not, that's not an N, is not significant because P of x is greater than 10.5 is not less than 0.05. And that's it. And then you would show your work, you would show that calculation. Well, that's how you would verify significance. But remember my previous comment, I mentioned that just because it's in the usual range, it could still be significant by the concept of significance. Let's look at the probability that x is greater than 11.3. So 11.3 is definitely in the usual range, right? We would agree. So by the usual range, we would say it's not unusual. It's in the range. But let's use the concept of significance. We would do 1 minus norm.dis of 11.3, given our mean was 9 and our deviation was 3, and always true. And that calculation actually worked out. Hold on, back up. Oh, 1.2. I put 3. I'm sorry. 1.2 is my standard deviation. I read that wrong. Hit enter, and look at that. That, in fact, is too big. It's 0.02. So that means that this is less than 0.05. So I meant too small. So that means that this is significant. It's less than 0.05. So by the concept of significance, I would say this is unusual because the probability is so small. It's so unlikely to see that extreme of a value that we would call it unusual, even though by the usual range, it's perfectly fine. 11.3 does fit between those two calculations. So it is fine by the usual range definition of usual, unusual, but it is not fine by the significance definition. And I made the same silly mistake on this one too, so let's fix that to 1.2. Deviation here, the calculation is still bigger than 0.05. And so yeah, so we should have had, the mean was 9, but the standard deviation was 1.2. I put 3 by mistake. But nonetheless, 0.10 is bigger than 0.05, so you would still not call it significant. But yes, the concept of significance does not always produce the same solution as the usual range method. So verify that. Okay, let's keep it going. Now we can go a little faster. So we're first going to identify our probabilities. So the probability says less than 2100. Now it says more than 3600. And then we see between, so smaller number, X, and then bigger number. And again, if you want the equalities for between, that's fine. You don't technically need them because it won't matter because equality turns to be 0, right? And then we'll talk about that one when we get there. So when we see less than, we know it's just norm.dis. When we see greater than, it's 1 minus norm.dis. And when we have two values, it's going to be norm dis of the bigger calculation minus norm dis of the smaller calculation. So let's do it. Norm.dis smaller, 2100, because it's this less than. Mean was 3420. Deviations 495. Always, always true. All right. 1 minus norm.dis. Observing 3600. Mean is 3420. Deviations 495. Always, always true. And don't be fooled. We know these are not exactly 0 or 1s. So don't be afraid to check your decimals as you need to. And you can see there it's close to 0, but it's not 0. When we have two numbers, we're going to do norm.dis of the bigger measurement. Given 3420, given 495, always true, minus the smaller measurement. 3420, 495, always, always true. Always big minus small when we have two measurements. And there we go. Okay, next one wants to know, is it usual or unusual? And notice they're not telling us to do it any certain way. And so again, we have two methods to determine whether it's usual or unusual. And notice they're asking you to justify your answer. That means they don't care which method you do, you just got to be able to support it or explain what you did. And so the first method is the usual range. And the second method is the concept of significance. And when they don't tell you which one to pick, you get to pick the method that you like and just go with it. Otherwise, they'll tell you using the concept of significance or using the usual range of values. You would then have to do it that way. But if they don't tell you, you get to pick. For this activity, I'm going to do it both ways. So remember, the usual range is the center minus 2 deviations, and then the center plus 2 deviations. And so we'll have a lower measurement and an upper measurement. And our center from up top here was 3420 minus 2 times the deviation, 495. And we have 3420 plus 2 times the deviation. And so the question is 4608 between these two values? Well, no, it's bigger, right? And so according to the usual range, we would say this is unusually high. And then if I were to justify it, I would say using the usual range. And then I would show my work. And that's it. Now, if I want to use the concept of significance, we know the probability. We got to figure out, am I going to do less than or greater than? And so we have 4608, and our center is our mean, and our mean is 3420. And so we can see that that's the center. We want this little right side, so we're looking for the probabilities greater than 4608. And so we find the probability is greater than 4608. That means we're going to do 1 minus, right? And so we would say equals 1 minus norm.dis 4608 given 3420 given 495, always, always true. And if I scoot the screen over, it will flatten out for us. So it's one nice line. Hit probability, hit enter, and the probability is 0.01. That is smaller than 0.05. And so by the concept of significance, this is unusual because it's less than 0.05. And so then I would say by the concept of significance. That's my justification. Sometimes these methods give you the same conclusion like it did here. They both say unusual. And of course I could say unusually high because 4608 is higher than 3420. But sometimes the conclusion's the same. Sometimes the conclusion isn't, which is why you got to tell them what method you did. You got to provide your justification. Like that previous page, I showed that sometimes one will say it's normal and the other one will say it's not normal. All right. We want to find the middle 80%. So we got two bounds, x1, x2, 80's in the middle. Well, the whole thing makes 100. That means that these two sides are each 10. Because 10 and 10 make 20, and 20 and 80 make 100. So from x1's perspective, what's to the left? Just 10%. So for x1, norm dot inverse, because I want a measurement, I want a weight. So if you want a weight, remember it's always inverse for any kind of measurement. And our probability we said was 10%. Don't even bother converting it unless you really want to. The mean was 3420, and the deviation was 495, I think. Yes, 495. And so that's my measurement associated with 10%. X2, from X2's perspective, it's 80% and 10%. In other words, 90%. Norm.inverse, 90%, given again, 3420 and 495. And there's our calculations. These are the measurements associated with trapping 80% in the middle. And if you want to verify your work, norm.dis big minus norm.dis small, and you'd get 80%. Reading bottom to top, as always, you can see that we're just going to find the probability of a z-score less than George's. So the probability that we get a z-score less than George's z-score, which is 1.21. And notice I didn't have to read anything above this part right here. All that previous stuff didn't matter. And so if I want to know what the z-score's distribution, remember the z-score can be modeled by the normal distribution with a mean of 0 and a deviation of 1. So I don't need this fact or this fact at all because we're talking about z-scores. So we would say when it's less than, we know to use norm.dis. Nothing special, no 1 minus needed because it's less than. The z-score is 1.21. The mean was 0. The deviation is 1. Always, always true. Because for z world, its mean is 0. Its deviation is 1. And that's it. 89% of the population uses less power than George. So George likes to use a lot of power compared to everybody else. Okay. Next one says calculate the probability that we're going to have a energy level between Steve and George. They want us to draw a graph this time. So it means we're just going to draw our normal distribution. We're going to label Steve and George numbers. Steve is negative 0.73. So we know for Z world, 0 is the center. Steve is over here somewhere, negative 0.73. And George was 1.21. My memory is terrible, so somewhere over here. And to show what we're calculating, we just draw and shade the area between them. This is what we want. We want the answer between these two bars. Well, if you want a probability that goes from negative 73 up until X, and of course, since it's between, we have two values, we're going to do the probability of big minus small, right?
Yeah.
So that means that we can do norm.dis of the bigger measurement, 121, given 0, given 1, given true. There we go. Minus the smaller one, norm.dis negative 0.73, given 0, given 1, given true. There it is. That's the probability of people who spin between those two amounts. So 65% of people do more than Stephen, but less than George. All right, more of the same. I'll let you read this one for a minute, and then I'll start talking. Okay. So we're being asked to figure out which of these, sorry about that, I clicked the zoom button by accident, 1 second. There we go. Which of these represents a z-score and which one represents a probability? So a quick refresher, we know that probabilities are always going to be between 0 and 1. And so looking at the two values, we see that one of them would be a problem if it's a probability. Namely, that one doesn't make sense. We cannot have a negative probability based off how we define probability. And so that means that if one of them has to be a z-score and the other one has to be a probability, then Tanya must be the probability and Mike must be the z-score. So notice both numbers could have been a z-score, but we're told that one person has a z-score and one person has a probability. Since we're told that, we know that the only number that makes sense to be a probability is the one on the right. Z-scores are measurements, and you can technically have any number to the left, any number to the right, so it can be negative infinity to infinity for any z-score. They're continuous data points. But probabilities are bounded from 0 to 1. Okay. Now we're being asked, if we have a normal distribution, we're going to assume that it should have told us that, but if we have a normal distribution where the mean is 0 and the deviation is 0.8, whose score is further from the mean? So we're being asked to compare two people. So in other words, we're asking for a relative standing. We already know Mike's score. Mike's z-score is equal to negative 185. That's his z-score. So what we essentially need is Tanya's z-score as well. Well, we know Tanya's probability, right? 0.45. And they didn't tell us, but we're going to assume that's a percentile. So we're going to assume that the 0.45 is on the left. On a real test question, they would tell you whether it's a percentile or on the left or on the right. You'd have to know that. We're just going to assume, for simplicity, that's on the left. If it wasn't, we would do 1 minus and make it on the left. So if I want a z-score, that's not so bad. We're going to invert from the probability. Probability was 0.45. And for z-scores, the mean is 0 and the deviation is 1. So it's tempting to use this information provided over here, but this does not refer to a z-score. It's some generalized mean scores about these I measurements up here. Z-scores are always defined as 0 and 1 for their normal distributions. And so when we're calculating it, we make sure we use 0 and 1. Now, how do we figure out who's further from the mean? Well, we're just looking for the more extreme z-score. We got negative 0.1 versus negative 1.85. So if our mean of a z-world is 0, the negative 0.1 is very close, and negative 185 is somewhere over here. And so the further you got to go is what we're looking for. And so in this case, Mike's score is further from the mean. Okay. Well, now we want the probability between two measurements. And so we know it's going to be the probability of the bigger measurement minus the probability of the smaller measurement. And the way number lines work, the more right you go, the bigger they get. So in this case, negative 0.1 is bigger than negative 185. So this would be our first value, and this would be our second value. Well, let's just say we messed up and we put the wrong number first. We didn't think about it. Negative 185 looks bigger. So let's just say we messed up and put the wrong number first. This negative 185, given that the z world is 0 and 1, always true, minus the other calculation, norm.dis, negative 0.1, 0, 1, always true. I want to compare that to doing it the right way. So let's switch these around with the bigger numbers first, and the smaller number goes second, negative 1.85. Look at these two calculations. You'll notice when we fix them to the right amount of decimals is they're exactly the same. The only difference is when you do it out of order is you accidentally get a negative. So if that happens and you go to write your answer in, just drop the negative. We know probabilities are 0 to 1, and so you know you can't have the negative. So putting it out of order isn't the end of the world. You just need to drop the negative. That's it. Okay. So now if we want to find a percentile, percentiles are probabilities from the left. And we said we defined 0.45 to be on the left. So in other words, we just need to convert that to a percent. And if you weren't sure, type your decimal, hit enter, go back to it, go to home, and change it to percent. And there's your percentile. So 0.45 is the 45th percentile. Not the worst thing in the world. Now, in the last part here, wants the actual measurements. And just to remind us, we have a z-score for Mike. His z-score was negative 185. And we got a probability of less than some number is 0.45. So we said less than because we're assuming it's on the left for Tanya. So we need to go from z to x, and we need to go from p to x. We talked about the z earlier, right? We talked about both of these actually. We did the chart, right? To go from z to x, we're going to say x equals our average. In this case, it's a negative, so minus our z times the standard deviation. Then our standard deviation is, oh, right here, 0.8. So 0.8. And that will be our actual measurement from the z. So equals, our mean was 0. Told us that on number 2, mean score is 0. And then minus 1.85 times 0.8. And there's our actual measurement. Obviously, you'd want to check your decimals just to make sure, but that's the measurement. And for the probability one, that's norm.inverse. When you go probability to measurement, our probability is the probability on the left, so 0.45, given our mean of 0 and our deviation of 0.8 from above. and close your parentheses, hit enter, and there's our calculation. So these represent the actual measurements. And you can see that his score, in fact, is further away from the center than Tanya's, confirming our earlier calculation. All right, some problem solving time. If you read the first part here, you'll notice something really important is missing. We got a normal distribution. We know the mean, but we don't know the standard deviation. We're missing this. So we know the center, that's 60, but we don't know how we're going to count in both directions, what our deviation is. We are given a nice fact, though. We're told that an observation of 64 is equal to a z-score of 1.45, that these are equivalent. Well, how in the world am I going to find the probability of this measurement then? I know I want to find the probability that x is less than 64, but I don't know the standard deviation. Normally it would be norm.dis 64, our mean is 60, and then I'd write the deviation in true. But we don't have that number. But fortunately, we know that 64 is the same thing as 1.45 in the z world. That means, as I showed you by the table, is that this probability is the same probability as finding z less than 1.45. Well, how does that help us? Well, for z, we always know its distribution, normal from 0 to 1. That's your mean and that's your deviation. We know all the information for that one, so we can totally get the probability. It would just be norm.dis 1.45, and its mean is 0, deviation is 1, and true. So we can get the probability of less than 64 because we know the z conversions. We know it's equivalent. And it just happens to be 0.93. Well, that's great. But now we're being asked in the very next question, well, what is the standard deviation, presumably of the one we're missing, of this one right here? Well, we can use our other facts that we know. We know any observation, in this case 64, is equal to the mean, which we know is 60, plus our z-score, which 64 is associated with a 1.45, right? 1.45 z, so we can say plus because that's positive, times our deviation. So there's some number here, times 1.45, that when I add it to 60, I get 64. Well, if this is 60, this has to be 4 in order to get 64, right? Because 60 plus 4 is 64. So we know that 4 must equal 1.45 times the standard deviation, which if you remember your old algebra from high school days, that means your deviation is nothing more than 4 divided by 1.45. And so if we convert that, we can say 4 divided by 1.45, and there is our standard deviation. So now we know it. And if we want to go back and verify that it works, we could have said equals norm.dis of the 64, given our mean is 60, and that 2.76 number. I'm going to click it because it may not be exactly 2.76. Always true. And notice, same probability. But nonetheless, we know our standard deviation. It's just this calculation right here. So now if we want the probability between two measurements, we know what to do, y'all. Norm.dis, bigger measurement, given our mean, given our deviation, always true, minus norm.dis, smaller measurement, given our mean, given our deviation, always true. And there we go. That's the probability. Now, more likely. That means which P of X is bigger? This is what we're being asked. Which probability calculation is bigger? The first one says a score higher than 61. So X is greater than 61 versus a Z-score less than negative 1.1. In my opinion, the one on the right is a little easier because it says less than, and less than means just norm.dis, right? Negative 1.1. For Z world, it's 0 and 1. For its mean and deviation, always true. Z calculation. For greater than, that means we have to do 1 minus because it's greater than norm.dis. Given 61, given our mean was 60, and our standard deviation was at 2.76 number, always true. Which one's bigger? I hope we agree that 0.36 is bigger than 0.14, so this event is more likely to happen. You're more likely to find something greater than 61 than get a Z-score less than negative 1.1. All right. Rapid fire now. Less than. That tells us norm.dis, nothing special. More than. 1 minus norm.dis. Between norm.dis big minus norm.dis small. Expected value. N times P, where N is our objects. P is our probability, and probability says more. So X is greater than 310, which means, because it's more than, 1 minus norm.dis. Keep going. We're looking for a distance. That's a measurement. So norm.inverse of our left-sided probability. And we'll come back to that one. And then we'll talk about usual range, which means center minus 2 deviations and center plus 2 standard deviations. So in this one, they're very explicitly telling you what method to use. They're saying don't use the concept of significance, use the concept of range, usual range. So let's get our calculations going. So less than means just norm.dis. The measurement was 177. Our mean is 250. Our deviation is 50. Always true. Kaplow. More than 1 minus norm.dis. Measurement now is 215. Given 250, 50, always true. And 250 and 50, of course, come from the very top here, the mean and deviation. Okay, big minus small. Norm.dis, the bigger measurement's 370. Given 250, 50, true. Minus the smaller measurement, norm.dis, 270. Given 250, 50, always true. Hit go, and there's our probability. Okay, for our D case, and don't forget, of course, these are all rounded. If we go back and adjust our decimals, we can see that they're not going to be those 3 exact calculations. So always check your decimals. But for our expected value question, part D, we know we need our N, which you're told is 20. And we need our P, which is going to be, notes here for myself. And so I need N times P, which is my expected value. And so let's see, P, it's greater than, so 1 minus norm.dis, in this case 310, given a mean of 250, deviation of 50, always true. So we get that calculation to get our P, and of course N times P, and then we round it to whatever level of precision they need us to round it to. So about 2 fly balls is what we would expect. All right, now we want to talk about our usual range. And so our center is 250 minus 2 times 50, right from the top information, and 250 plus 2 times 50. So this is our lower bound and our upper bound. And so we would expect baseballs when they're hit in the game to be anywhere from 150 to 350. Anything in that range is usual. Anything out of that range is unusual. And so that's how we would determine what's considered a usual event by the usual range. So they're telling us exactly which way to solve it. All right, we'll find the probabilities in a second, but let's actually do the drawings. We've been doing a lot of those. So we would draw rough shape of a normal distribution. Dead in the center should be our mean, which we can see is 6. We're trying to see less than 5. 5 is over here. Less than means to left. So there's my drawing. And we know that whenever we see less than, we're going to just do norm.dis, nothing special. On the next one, rough sketch. You don't need to draw anything pretty. In the center is 6. 5.5 is smaller than 6, so it's over here. But now I see it's greater than, so I draw on the right. All this is my shaded picture. When it's greater than, because that gives it to you on the right, we need to do 1 minus norm.dis. Okay. Third drawing my shape. Putting my distribution. You'll see that I drew it poorly all 3 times. That's okay. Let me make that a little nicer though. Something to that effect. In the center is my 6. And I want to go from 6 to 7. So 6 to 7. And I want the X to be in the middle. So I'm going to draw it, but shade it between the 2. And so those are my drawings. When they say draw the graph, this is what they're talking about. And when we have 2 measurements, we know to do norm.dis of the bigger measurement minus norm.dis of the smaller measurement. So let's do our calculations. Less than, so that's just norm.dis. Measurement in the parentheses there is 5. The mean was given as 6. The deviation is 0.4. Always, always true. And yes, I will make my font larger for us. Click on that again, and there you go. So the 5 from the question itself, and then 6 and 0.4 came from the paragraph above, and always true. The second calculation was this one up here. I'm just going to try to move it back. Whenever you increase your font after you draw, it does this weird jumbly thing. I can actually group them. Anyways, you get the general idea of what's going on here. I hope we're just going to move this back up though. So now that I want greater than, of course, what does that mean? It means I want to the right. So I'm going to be doing 1 minus norm.dis once my OCD is happy and I move all this back where it goes. There we go. Okay, I'm happier now. 1 minus norm.dis. Measurement was 5.5, given 6, given 0.4, and always, always true, right? There's my probability of being greater than. And then when we have 2, we know to do the big minus the small. So norm.dis. 7 was bigger, given the mean was, number I forgot, 6, and 0.4, always true, minus norm.dis of the smaller measurement, 6, given the mean was 6, 0.4, always true. And there we go. That would be the probability between those 2 lines. All right, last question for the day, my friends. And I know if you need to go, you need to go. That's absolutely fine, but I'll finish this last problem for us. It's more of the same. Let's see if you can do this ones without having to write everything out. Lower means, of course, it means less than, so it means I'm going to do just norm.dis. Norm.dis. Lower than what? Lower than 165. What's the mean? The mean is 178.1. What's the deviation? 40.7. Always true. There we go. Okay. Higher than. Higher means greater. If it's greater, we have to do 1 minus every time, no matter what. If it's greater than, 1 minus when you're using norm.dis. So norm.dis, greater than what? Greater than 255. Given our mean, given our deviation, always, always true. Between two measurements, okay, we know what to do. The big measurement, 160 or 200, which one's bigger? 200's bigger. The mean is 178.1. Deviation was 40.7. Always true, minus the other measurement, norm.dis, 160, given 178.1 and 40.7, and always, always true. And there we go. Of these three events, which one is most likely to happen? This bottom one. This one is the highest probability, so it's most likely to find somebody with a cholesterol at that age range between 160 and 200. Least likely to find somebody with cholesterol higher than 255. And you can notice that calculation is in fact significant, which means if you found somebody with that cholesterol, a number higher than 255, it'd be a red flag that there's something going on with them. Maybe they got high cholesterol. Maybe they have heart disease. Maybe they just have naturally high cholesterol. We don't know. We just know something is unusual about that score. And so we would need further investigation, more lab testing and that kind of stuff. But yeah, that's norm distribution in a nutshell. Next week, either this Saturday, when I say that, or coming Tuesday, I will be talking about CLT. And then you also should get an email talking about the first, second, and third being my test review days. Each day is different content, so I encourage you to sign up for all three if you haven't done so. But I'm also hosting them in person as well, if you prefer in person as opposed to online. But that's everything. I am going to stop recording.